Alright, in this two-part lecture, we're going to try and understand the big O notation. Here's the definition, which is quite complicated. So we'll work towards this definition and kind of try and understand things intuitively as we work our way towards this definition. Now, just so you know, so we have an idea of what we're doing, it's all about comparison. Let's say that somebody suggests a place to go eat dinner tonight, and you say, well, how expensive is it? They might tell you, well, it's not as expensive as this place, but it's going to be more expensive than such and such a place. See, we do this all the time. We interpret new information by comparing it to information we already have. Now, with functions, sometimes we might be interested in how fast functions grow. For example, with algorithms, you might be interested to know how complicated an algorithm gets. How many steps does an algorithm make? Let's say that there's an algorithm that sorts 10 numbers. You follow certain steps to sort 10 numbers. You might be interested to know, well, how many steps will it need to make if I'm going to sort 100 numbers? What about 500? What about 1,000? See, so you're kind of interested in knowing how complicated an algorithm gets down the road. In order to have a sense of that, we need to be able to compare functions. Okay, so the big O notation is all about comparing functions. In particular, it's interested in how fast one function grows compared to another. So I want you to think of the tortoise and the hare. Okay, the hare moves quickly and the tortoise moves slowly. So we want to come up with a way to look at functions. Okay, two functions, and be able to call one the hare function and the other one the tortoise function. In other words, one function grows quickly and the other function grows not as quickly as the hare function. Okay? So that's what we're interested in, which function grows quicker. Now, how do we formalize this? What condition can we give to be able to assign one function the hare function, the fast-growing function, and the other function the slower-moving function? Well, you might say, why don't we say that the hare function will be the function that's greater than or equal to the tortoise function? Okay, if you have two functions and one of them is greater than or equal to the other function, we'll call that the hare function. Let's take a look at a picture. Here we have two functions. Now, which one of these moves quickly? Well, if you look at the picture, this one has a lot more pep in its step than this top function. If you look at our definition, though, according to our definition, this slow-moving top function is going to be the hare function because at every point it's greater than our tortoise function. See, we messed up. Our definition doesn't cut it. Looking at these functions, clearly this bottom function moves quicker. We want to call this our hare function, but according to the rules that we made up, that's not the case. Okay? So this doesn't cut it. Our first try was to say, okay, call the hare function the function that's greater than or equal to the other function. But this gets messed up if one function's pointing in the other direction. I don't really care about positive or negative. I just want to know which function grows quicker. So if I don't care about positive or negative, there's a quick fix to this. We introduce absolute values. Now, I'm not looking at any negative values. I don't care about negative. I'm only interested in magnitude. So let's take a look at the picture. Here are old functions from the first example. Okay, I called the bottom function f and the top function g. Notice what this looks like when we introduce absolute values. Now we're cooking. Now we're on the same page with both functions. You can clearly look at this example and say, okay, this function, this is going to be my hare function. It moves a lot quicker than the other function. Right? So this is what I'm going to call my hare function. So the absolute values help put things on the same page so that you can compare apples and apples. There's an issue, though. Notice that, give me a second here. Notice that, according to our definition, the hare function is just a blanket statement, has to be greater than or equal to the tortoise function. Look at all the values below 2, though. If you look to the left of this line, where 2 is, you'll notice that the blue function, which obviously grows quicker than the red function, this blue function is actually less than or equal to my slow function. So, but does that change things? Not really. If I'm interested in how fast a function grows, I'm just interested eventually. If there's a turning point down the road somewhere where one function is and remains forever greater than the other function, I don't really care what happens in the beginning. Okay, with algorithms, for example, I don't really care how many steps you take with small values. I'm thinking big picture, I'm thinking down the road. So really, what we mean is we want this to happen. We do want our hair function to be greater in magnitude than our tortoise function, but we mean eventually. We mean down the road. Now let's look at our picture. At 0, my hair function is actually less than or equal to. Alright, see, my blue function is less than the red function, less than or equal to the red function. At 1, my blue function is still less than or equal to my red function. But after 1, my blue function is in fact greater than or equal to in magnitude than the red function. Okay, so really what I want to say is ignore 0 and 2. Just start looking after 2. After 1, I mean. So formally, well, let's say after x equals 1, this inequality is true. In other words, for x greater than 1. So I'm saying ignore all this stuff and just start paying attention after 1. So start paying attention at 2. So this might feel like cheating, but it's not, because remember, when we're interested in growth, we're just interested in down the road. We don't care what happens initially. So because of that, I say, okay, ignore everything up to 2. So only start looking after x equals 1. Okay? So that's where that comes into play. Let's do a little recap. Oh, and also notice that if my blue function is greater than or equal to my red function after 1, so starting at 2, notice that it's going to be greater than or equal to after 2. After x equals 2. It's going to be greater than or equal to after 3. It's going to be greater than or equal to after 4. Anywhere over here, and after any of these x values, my blue function will always be greater than or equal to. Okay, so the definition of big O notation doesn't say find the smallest number where it starts to work. It just says after some number. Okay, so I could say after x equals, or for x greater than 1. I could have just as easily said for x greater than 2 or x greater than 3, x greater than 10. It doesn't really matter. You got to think big picture. Just as long as after some point, you can say for certainty after this number, my hair function is going to be greater than and stay greater than my tortoise function, then we're in business, okay? So let's do a little recap. Big O notation. Our first try was, let's let the hair function be greater than the tortoise function. That failed, okay? It doesn't work. Because if you're pointing in opposite directions, you might end up calling your slow-moving function your hair function, and your tortoise function might grow a lot quicker. So that was a bomb. So we couldn't do that, so we said, okay, let's introduce absolute values. This was a lot better. The only thing that happened when we introduced absolute values is that there was those initial values that kind of threw us off, but we don't care what happens at the beginning. We just care that at some point and eventually, our hair function is greater than or equal to our tortoise function. So we had to formally say that. Well, really what we mean is the hair function should be greater than the tortoise function in magnitude eventually, after some point k, and mathematically we just said whenever x is greater than k. That's all that's saying. Whenever x is greater than k may look cryptic when you first look at the definition, but it's just saying at some starting point, in this case it happens to be k, at that starting point, after that, no problem, our hair function is always going to be greater than the tortoise function in magnitude. Okay, so we came up with some pretty good criteria to be able to concretely, rigorously define when one function grows quicker than the other function. Oh, that we were done, but we're not. There's one piece that we're missing. Let's go back to the definition of big O notation. We talked about why we have to introduce the absolute values. That's not that big a deal. We talked about why we have to introduce this k business. That just means that we're interested at eventually, after some point. What we haven't talked about is where this mysterious c comes from. Why do we throw this extra constant into the mix? Well, to answer that, you're going to have to watch part 2.